Now, a proxy firewall is different than a proxy server, and I've found some people get these two mixed up. A proxy firewall is a firewall. You actually have rules that it's going to look at the packet, make a decision on, and then it's going to change the header information to its IP address and send it on. Or a proxy server, you can have some type of rules, but it doesn't provide that level of protection. You usually have a proxy server where anybody who wants to go to the web, the internet, they have to go through this proxy server, and that may be where, like, you're doing some type of content filtering or looking at the type of traffic, but a proxy server is not a proxy firewall, so don't get those two mixed up. Now, a stateful is another type of firewall that's a third generation, and before we actually get into what a stateful firewall does, we have to understand what state means. If something is stateful, it means that it's keeping track of how communication takes place. So when I was talking about TCP, there's a three-way handshake. The first packet is SYN, then there's a SYNAC, and there's an ACK. Now, if something's stateful, it actually keeps track of all those three handshakes, and it knows how the handshake is supposed to take place. So that means that if a SYNAC comes in and the first packet never actually came in, which is supposed to start the communication, it won't be fooled. So it's not going to be fooled like with a packet filter firewall where somebody could send a SYNAC and the firewall can assume that there's already a communication going on because that's in the middle of the communication. Something that's stateful will remember, it's going to actually keep track. And in a stateful firewall, it has a table, and it's going to be populated. So let's say that I send a packet over to you. It's coming on TCP, and then it's going to, the stateful firewall will look at its rules, compare it to what I'm sending. If it's okay, then in its stateful table, it's going to document my source IP address, my source port. It's going to document the destination IP, destination port, and there's other sequence numbers. It's going to document basically everything about this packet. And so then the packet goes over to you. Now when you reply, that would be a SYNAC. And the stateful firewall is going to be, wait a minute, you can't just send over a SYNAC. Has there been a communication? Did somebody actually start this communication with you? So it'll look at the stateful table and say, okay, this matches. The IP address and the port number matches what this packet's going to, and the sequence numbers. So it keeps track of all of the communication going back and forth. It's easier, of course, to do it on a connection-oriented protocol, but it keeps track of connection-less protocols also. And connection-oriented just means that, like TCP is connection-oriented, where there's like a constant ACK that goes back and forth. So once we go through our handshake through TCP, we're actually sending acknowledgments back and forth, and that connection-oriented protocol will know if there's a packet missing and resend it. Versus a connection-less, which would be like UDP, I could send out a packet and that's it. We're not doing any handshaking, we're not doing any acknowledgement, and so there's not as much state information to keep on a connection-less, but the stateful firewall will actually keep track of everything. Because what happens at the end of a connection-oriented session, let's say you and I are communicating over TCP, so when the communication is done, when we're done talking to each other, I send over a FIN packet and you send over a FIN packet, which is finished. And so the state firewall knows to go ahead and erase that out of the state table. Now, a connectionless never sends over a FIN, because there's no connection actually, set up. So what it does is it times out. If the using like UDP. If there hasn't been any traffic over these IP and source numbers for a specific amount of time, then it'll assume that that connection is done and take it out. So stateful firewalls, the benefit is that they understand how the protocol communication takes place, and they don't get into the application layer for every packet. A lot of times the stateful firewall will look at all of the information of the first packet of the communication, and from there on it will just look at the like the network and the transport header information. So like I said, the stateful firewall is going to have its own state table. The administrator is going to configure the rules, who could talk to who and how communication could take place. And that's different than the state table. The state table is basically a scratch pad for the firewall to keep track of each communication going back and forth. So far we've looked at packet filtering firewalls, network header. We looked at the stateful inspection, which is keeping track of the sessions, and application proxy firewalls, which is getting into how the protocols are being used, how the actual command syntax of every protocol that's coming through. And what's interesting is that, in my opinion, and I may be a pessimist, but we're never really going to get away from attacks. These are always going to happen. Because if you understand how a lot of the attacks take place and are successful against the network stack, you see that it's very difficult to plan for what's next. What else is the bad guy going to think of? Because in just the network header, there could be what's called a land attack. And the source, that means the source IP and the destination IP are the same address. So it's been manipulated, so the source IP and destination are the same. Well, when the developers wrote the software for this network stack, they never expected a packet to come with the same address, because there's no functionality. That doesn't make any sense. So that would be a vulnerability, and some systems would freeze up or they'd reboot. And a lot of the attacks that have taken place, especially the older attacks, has just been flipping bits in like the headers that isn't how it would work. Like for the old attack, it's called an Xmas attack, where all the bits are actually flipped. All the flags are turned on within the TCP header. And in no way would that ever happen. There's no reason for that. So the software was developed not to even deal with that, or not to look out for that. And so that's just in the network header. We also have the whole keeping the state of the steps of the protocols. And there's, people come up with different ways of injecting traffic into steps, or tunneling through protocols. And so there's a lot of things that it's hard to think of everything that people will do. And then you get higher into the application, and remember, we're talking about a network stack. We're not talking about actually applications. At the application layer, those protocols, there's a lot of attacks that take advantage of those. And it's because that it's very difficult to think outside the box. I mean, developing is difficult enough, and to have all this functionality work, but then to think about all the goofy things that people are going to create and throw at your system, that's why I think that we're always going to have we're going to have some type of attack. But that's why it happens in the network stack, is because the protocols are set up to do communication. That's what these fields and these values are. They're so that one system can understand the other. And when other flags are turned on, they just don't know what to do. They haven't been programmed to understand that, and that's why it's a vulnerability. So the 5th generation is called a kernel proxy firewall, and what that means is, well, there's 2 specific things that make it different. First, the actual packet will go into a kernel. It's not going into software. when you have a firewall and it has to go into the software portion for to be filtered or to be compared to some type of security rules, that takes longer than if it actually takes place in the kernel. And another thing that happens within a filter, or a kernel proxy firewall, is that it will create a virtual network stack for a specific protocol. So let's say that a packet comes in. Let's say it's coming over HTTP, and what the kernel proxy will do is build a network stack with the necessary protocols and the information it's going to look at, and compare it to that proxy. Compare it to that packet. So it's actually going to, based on the packet that's coming, it's going to build a network stack, a virtual network stack, which is basically the virtual rules that each of the headers are supposed to match against, versus the other ones just have like a list of rules. They're not dynamically going to be built based on what's coming over to it. So a lot of the firewalls today have VPN capabilities. It just means that VPN technology has been built into the firewall. VPN allows secure transmission to take place. We'll go over that later in this domain. We'll talk about PPTP, IPsec. But when it comes to the firewall, what the benefit is that when the VPN will actually end, which means that if that data has been encrypted, it'll be decrypted, and then the firewall will apply its security rules right away. Instead of having a VPN device that will decrypt the data and then have to send it to a firewall, it'll go over that line unencrypted, they're actually combined. So what are some of the things that we need to be aware of for firewalls? Well, we should block the ICMP redirect traffic. ICMP is a network protocol that has several different types. ICMP is a protocol used specifically to have error messages and have status information. It's not developed to move user data back and forth. So you would want to block the ICMP redirect traffic, because there's attacks that will actually tell like a router to redirect its traffic to another router. You should not allow source routing, and there'll be an actual rule that you have to write out, like in an ACL, that says don't allow source routing. And what source routing is that the packet actually makes a determination of what hops, what routers it's going to. And you don't want that. You want your routers to control the traffic in your network. So a source routing packet will actually override your network configurations. So you need to make sure that doesn't come through the firewall. Disable unused ports and services, disable unused interfaces. You also do not want to allow any packets that are coming in with the same address that you use within your internal network. Why would that be? Well, if you have a packet that's coming in that has the same like one specific address that's in your network range, your IP range, that means that somebody spoofed that packet, because there should be it should be coming from a different network range. So that's a giveaway that somebody's actually spoofed that address. So you want to not allow that. And there's a lot of things that you need to configure and understand, that you want to ensure that broadcast data can't come through, because that could be a denial of service where broadcasts continually come through the firewall into the network. And you want to enable logging. The more logging, the better. And you don't want to use like freeware administration tools, because it's freeware. It's not that they're necessarily bad, but a lot of companies actually use VNC, which is free and allows you to do remote administration, but it could be easily broken. There's a crack for it. I've done it when I was in the information warfare unit. So you have to make sure that your remote administration of the firewall is secure. So we've talked about the different kinds of firewalls. Now where do we put them? Well, that's the architecture part that we're going to go through. And again, what we're going to talk about is kind of a straightforward, very simplistic types of architectures, and they can get very complex within large organizations. Now, I've been talking about firewalls, and we'll keep talking about them as though they're just connected to the internet, like we say, talk about the DMZ and such. But it's important to know that firewalls are used throughout the network to be able to segment different network segments. They should be not just about the internet. Any type of remote access should be going through a route or a firewall. So they're used throughout the network, and they should be. But a lot of the talk that I'm doing, because of what you'll see in the exam, is more about the firewall types and the firewall placements when you're connecting to the actual internet. So we'll look at 4 different types of architectures: packet filtering, screened hosts, dual home firewalls, and screened subnet. So the packet filtering architecture is actually one that's kind of new to CISSP. They had the other 3 for a long time, and now they've added packet filtering, which just means that you have a router with ACLs, and then it goes directly into your internal network. So if you just have a packet filtering architecture, you have a packet filtering firewall, and whatever untrusted network, the internet or traffic's coming through, it's just making decisions based on the header information, and then bam, you're right into your internal network. Now, a screened host is actually different. It provides a little bit more security, where you have, like the router, the screening device, and that's usually a packet filtering router. So you have your screening device, and then you have your screened host, and it's providing 2 layers of protection. So in a screened host architecture, it's not just one layer that's protecting before you get to the internal network. You have a packet filtering firewall or some type of screening device, and basically that's going through and getting rid of the obvious traffic that's not needed, and then it'll go to the screened host, which is usually the firewall, and then that data can go into the network. So there should be no traffic that goes from the screening device into the internal network, or from the internal network into the screening device. All data needs to go through internally, it needs to go through the screened host, and then out. If it's coming externally, it needs to go through the screening device to the screened host, and then into the internal network. Now, another architecture is called dual-homed firewall, and the CAN definition is that it's a firewall with 2 or more network interfaces. And most of us know that almost every type of firewall has at least 2 network interfaces, because it's connecting to at least 2 different types of networks. And that's the CAN definition, is that a dual-homed firewall is one with 2 or more interfaces. But what this means is that you'll have interfaces that you can actually build other DMZs on. And a lot of organizations will have a DMZ that has maybe just their web servers, and it'll be under a specific IP range, and then they'll have another DMZ with maybe their DNS and their mail server, and it'll be under a different IP range. That's because if a hacker gets into one of them and figures out the IP range, it doesn't mean that they automatically can get into the other DMZ. So you can have a dual-homed or a multi-homed firewall, which will allow you to build DMZs, basically logical DMZs, off that one firewall. Now, a screened subnet is actually creating basically a physical DMZ. You have a firewall, and then your servers, and then a firewall, and then your internal network. So this is one of the most common architectures that's used in the industry, where you'll have a firewall. Now you may have a screening device before that, but what a screened subnet means is you have firewall, and here is the DMZ. Those are where all the systems need to be bastion hosts, which means they're locked down, and only the systems that have to be there. We talked about like external mail server, external DNS server, your web servers may have to be there. Now, another thing with a screen subnet is some companies, to provide even more security, will ensure that those firewalls aren't from the same vendor. Because if there's an exploit for a firewall, product, and I'm a hacker, well, I can get through the first firewall and then I can get right through the second firewall because they have the same software. So some companies use one vendor for one firewall, another vendor for another firewall to make sure that that doesn't happen. Now, when the traffic's coming through in a screen subnet, that first firewall will have kind of looser rules because it's got to allow data to go into the DMZ systems, but then when it goes to that second firewall, they're tighter, meaning that it only allows traffic to go into the internal environment. So the screen subnet actually provides the most security out of the different architects we've talked about. The packet filtering, just one layer. You just have to get through that packet filter firewall. Screened host, you have to get through the screening device, the screen host to get to the internal network. In a screen subnet, you have two firewalls that you have to penetrate before you get into the internal network. So it provides more security, more layers or barriers that the attacker has to get through.